Welcome to the office. We want to take a look today at what is actually an exercise from the book that I'm using because it's very useful in terms of deciding potentially if there's not a homomorphism between two groups, or at least not anything other than the trivial homomorphism. We certainly mentioned that the trivial homomorphism exists for every pair of groups. So let's say we have some function phi that is a mapping, a homomorphism from G to G prime. We want to show that if G is finite, okay, so this is a finite group, then the image of G is also finite, and that the order of that group is actually a divisor of G. Interesting, interesting. This theorem seems not quite so obvious, right? If this said the image of this is finite and divisor of the order of G prime, that would be pretty simple and straightforward. And that's actually an exercise that I would like you to take a look at, right? In that case, we actually assume that G prime is finite and that we want to show that this thing is a divisor of the order of G prime. Okay, so you should take a look at that. Here, what we want to do is, of course, consider the form as it's given. Now, there's a fair bit going on to this problem. So I'm going to approach it by telling you some of the things that we do. I'm not going to work through all of the details of it, just to try and keep things relatively short here, but kind of give you an outline of how to approach this particular problem. And what we would do is we would begin by considering an equivalence relation. So consider the equivalence relation where x is related to y if and only if phi of x is equal to phi y. So these are elements in G. So this is an equivalence relation on G. You should verify that this is an equivalence relation. Okay, I'm not going to work through all the details now, just to save us a little bit of time. All right. The set of equivalence classes is the next thing that I want to consider. So the set of equivalence classes. So what I can do is I can say I have these equivalence classes, and let's let them be a set, the set of equivalence classes. I'm going to call that set E. These things define a partition of G. Now, since G is finite, right, we're assuming that G is finite. Since G is finite, the number of equivalence classes must also be finite. Since G is finite, the number of equivalence classes must also be finite. We have a partition. I could partition every element into its own set. That's the most number of sets that I could create that would define a partition. Therefore, we must have a finite number of partitions. Or sorry, a finite number of sets defining our partition. Because of that, we can let E be defined in this way. We have our first equivalence class, we have our second equivalence class, we have our third equivalence class, all the way up to our kth equivalence class. Oh, I'm sorry, mth equivalence class. So E is equal to m in this case, a finite number. All right. Now, if we wanted to, we could consider a map, a function f from E into the image of G. Oof, that seems a little bit weird. I suppose I use brackets there. So what we're doing is we have this set of m elements, and we are going to map them into phi of G. So we're technically mapping them into G prime, really. But what I'm trying to do is I'm trying to point out the fact that these two things must be the same. Everything in here maps to the same thing, right? That's how I'm defining this equivalence relation. A1, B1, C1, D1, all of those map to the same thing. A2, B2, C2, everything in here maps to the same thing. So what we get is that however many things there are here is exactly how many things there are over here. So then if from there to there, defined by, let's go with f of a1 is equal to phi of a1 is a bijection. Now, again, that's another thing I'm not going to go through all of the details of, but that should make sense to us for the most part. And if it doesn't, I would encourage you to kind of double check it and see, well, how does that work out? Why is that a bijection? Because you should be able to find that it is. So F is a bijection, hence the number of elements in E is the same as the number of elements in phi of G, which is M. Hey, so we got this part. The image is finite. The image or the range denoted by phi of G is finite. It is a finite set. Excellent. It itself, of course, is a subgroup of G prime. That's wonderful to know. So far we have that this is finite, but we also now want to show that this number m is a divisor of G. So how does this work out? All right, let's consider. It works out pretty nicely here because one of these things is exactly associating to the identity, right? For one of them, phi of AI is E, which means that one of these is the collection of elements that maps to the identity. That should sound familiar, right? That's the kernel. So one of these equivalence classes is exactly the kernel. Now, let's consider the left cosets of the kernel of phi. Now, I've said in words that one of these is the kernel, but I've not written down that one of these is the kernel because that's going to be a little bit difficult to observe easily. Or I can say it, it makes sense, but I think writing it down, well, actually probably wouldn't be that bad to write down. So maybe we could have put that in here somewhere. AI is the kernel of phi for one of the AIs. I don't know which one. All right, so let's consider the left cosets of the kernel of phi. So A times the kernel of phi for some A in G is equal to, by the definition of the kernel and by the definition of left cosets, So really left cosets here is the definition I'm looking for, is A times K, where K is some element in the kernel of phi. Cool, that's just the definition of a left coset. But let's utilize the definition of a kernel for a moment. This being the kernel means that phi of K is equal to E. Now let's write it in terms of AK. Well, what we're really interested in here, so it's all of the elements AK. AK is an element in G. It's all of the elements AK such that phi of AK is equal to, well, that's phi. We don't need to write all of this out, skip this middle piece here, but we should recognize that that's phi of A times phi of K, but phi of K is just E, so boom, gone. There we go. We just need this right here. Now, we can recognize that any element can be written as a multiple of K. So this is some side work, a side note. So let's let G be any element in G. Any element in G. So us saying AK is relatively arbitrary. Really, we're talking when we restrict our viewpoint to all of the things AK, well, we're not restricting our viewpoint at all. That's everything. AK is everything. Everything can be written as a multiple of A. So what I want to do is I want to recognize that G, of course, is equal to G. See, is this the way that I want to go about this? I think that it is, but apparently I forgot to write it down. So let's take a look. G is equal to G. I don't think anybody is going to disagree with that. What do I want to do at this point? Oh, I want to write G as a multiple of A, where A is on the left. Okay, fantastic. So let's multiply by E. Well, I can always multiply by E, but E is A times A inverse. But I can regroup that. So now I have G can be written as a multiple of A. Ta-da! So I'm trying to write this down so that way we can understand that this allows me to move to any generic element in G where the image of G is the same as the image of A. But this is exactly the definition of our cosets. Or sorry, yes, that's what I started with was cosets. I'm sorry. That is exactly the definition of our equivalence classes. Equivalence classes are all of the things G that have the same image as that, right? This is the equivalence class containing A. That's awesome because we get that these, so thus the cosets of the kernel are the equivalence classes of R. Why is that good? Well, we already know that when we talk about cosets, each of the cosets has the same number of elements in it. So we can say the size of each coset, that is each equivalence class, may be expressed as, well, it doesn't really matter. It's just the size of the kernel of phi. But again, because of our understanding of cosets, we know that the kernel of phi being a subgroup, we have that the size of this subgroup multiplied by the number of cosets gives us the order of the group that is a subgroup of. Kernel is a subgroup of G. There is an integer m such that kernel of phi times m is equal to G. And that m is exactly the number of cosets, which is exactly the number of equivalence classes up here. So in particular, m, where did we say it here? That's this thing. Size of the kernel times the size of the image of G is equal to the size of G. That is the size of the image divides the size of the group. Oh, that's so cool. That's so cool. That was a lot of fun. Okay. It took a little while for me to figure out how to approach that problem. It's quite interesting. Okay. I have, of course, I've got a little bit of background, so I'm like, okay, how can I use this, background knowledge that I have? What does this work out to be? So this was a really fun problem to approach. I think this would have been really difficult for a student to approach and approach it quickly and easily. Right? This is something that's accessible to maybe the super interested student, but not the easiest thing ever. So that might make you reflect on, well, Dr. Reinhardt, what about that case where we have that you asked us to take a look at, where we show that if G prime, right, the order of G prime is finite, then we want to show that this is finite and is a divisor of the order of G prime. Is that tough? No, that's actually a lot easier of a problem to address. It works out for a lot of the same reasons, right? You just need to consider whose theorem is that the order of a subgroup divides the order of the group, and then reflect on at the same time the properties of homomorphisms. And that's actually going to be enough. Lagrange's theorem popped to my mind, right? Lagrange's theorem says that the order of a subgroup divides the order of the group. And so we just need to recognize the things that were given along with the properties of group homomorphisms. And I mean, it falls right out almost immediately. So very, very short in comparison. But that's all that I wanted to share for now. So thank you for your time and attention. We'll look at some more examples actually in our next video. So I'll see you shortly.